Hello. Hi, good evening. Hello, Supriya. Okay.
Hello.
Hello, hi. Yeah,
Good
so
evening.
yeah, what did you say?
Good evening.
Yeah, good evening.
Good evening.
So I think others have not joined, so we'll wait for another 1 or 2 minutes and let's see if somebody else joins and then we'll start like
Yeah.
usual.
Okay.
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 Okay, so maybe we can start. So good evening once again, and welcome to today's session on urban utilities planning, water supply, sanitation, and drainage. Both of you have been attending all the classes, so let's just proceed ahead. So this session, we will discuss about certain assignment questions and problems dealing with the topics which we learned in week 8. So week 8, we mainly learned about water carriage systems and sewerage layout. How do we plan them? The quantity of sanitary sewage. So mainly there was a lot of focus on sanitation. And then the last part, 3 lectures were dedicated mainly for stormwater drainage. What are the different methods that we use? We did not go into detailed calculations for those, which we will be dealing in our next module, that is week 9. So this mainly about the theory part and the different data that is required, the different methods that we use, all the overview we learned in this week's lectures. So yes, so we'll try to solve previous assignment, that is last year's assignment questions based on what was discussed in this week, so that this week's assignment you will be able to solve it easily. So yeah, so this you already know, so let's just directly go on to our first question. So first question is match the following and mark the option for the correct match. So this is directly from one of our lectures. So I think Supriya, can you do you want to attempt this question?
Yes.
Yeah.
A is 2
A is 2, yeah, correct.
and B is 3, C is 1.
Separate
A
system.
option.
Okay, so separate system is yes, and C is yeah. So this is yeah, A option. So this is correct. What you said is correct. We have, I mean, it's a very direct application. So we have learned that carries both sanitary sewage and stormwater, and separate system you have separate sewers for that, and partially separate system you have a portion which is dedicated. So now which is more preferred? That is, if you have heavy rainfall, then which is preferred? Uh, Combined, separate, or partially separate?
Yeah, for heavy rainfall, separate system is better one.
Why?
As because for rain for drainage system will be designed as per the rainfall.
Okay. And in terms of cost also, it'll be much easier because a combined system you'll have to build so many for and both sewage and stormwater you'll have to consider for that, and the requirement, the investment that you'll have to put in will be more. So eventually, if it's a heavy rainfall area, then a separate system is better. Okay. So yeah, so
I lost the network.
sorry.
Yeah, I lost the network. Sorry for that.
Okay, okay. Yeah, so is there any doubt in this question? Shall we proceed ahead?
Yes.
Yeah, fine. So next one, sewage lines are installed in a vertical zigzag configuration in which of the following? Pressurized sewer system, vacuum sewer system, partially separate system, and combined system.
It's vacuum sewer system.
Okay, Supriya says vacuum sewage system. I think Shripad has joined. Hello, Shripad. Shripad, what do you think about this? Shripad, are you around?
Hello, good evening. Good evening,
Hello,
madam.
hi, good evening. Uh,
This is vacuum system, madam.
okay, great. So, Supriya, do you want to say why do you feel it's vacuum system? Okay, we've learned this. That is, sorry, I went to different side. Yeah. So we learned this that in vacuum system, it is arranged in a zigzag manner. But any observation or reasoning why this is done? Uh, Hello, Supriya.
Yes. You can explain. I can't say the
Okay,
reasoning.
okay,
Madam,
okay.
in the vacuum system generally installed in the areas where there is already congested areas or existing city where there is no slopes are followed. So that's why uh, uh, mainly the sewage is supplied to the main sewage treatment plant by the vacuum system only.
Hmm.
So there are some collection centers.
Yes.
Okay. So this type of design is feasible for the vacuum system.
Yes, yes, you're right. So yes, so you have separate you have separate uh, stations where you collect and then you pump. But my question was, why is it in a zigzag? Like, why couldn't it be diagonally, or why couldn't it be in any other form? So yes, partially the answer that you said is right. So it has limited capacity.
So
Like,
friction losses to reduce maybe the friction losses.
Exactly. So yes, friction losses also come into play because the whole concept of vacuum is that you are pumping this out. That is, the pressure which is there is inside this vacuum pump or the vacuum sieve is lower than the atmospheric pressure or the pressure which is there over here. So we know that when there's a low pressure which is created, it automatically the sewer gets attracted, or water, whatever is there, it's getting pulled. So in that, when you're diagonally putting like that, sorry, it's not, yeah, more than that, when we put a zigzag configuration, it easily gets attracted. You can push it and then it goes up a bit and then you pull it again. So it's used for that particular purpose. So here from the CPHEO, they've given the reason for this. So in a previous slide also we discussed this. The main reason is that these sewers can take advantage of the available slope, but still the lift or the pull water uphill or the height, it is restricted to up to 9 meters. You can't go more like that slope. You cannot take a deep slope and pull it up. And so the working principle also, once we learn understand that, we will be able to reason it out. So basically this is what I was explaining. Every valve pit is fitted with a pressure controlled vacuum valve, which automatically opens after the predetermined volume of sewages enter the sump. So the sump is where you collect it, and then from there it goes. And so this is the difference in pressure. So because of the difference in pressure that is in the vacuum line or the main, that the pressure is much lower than the atmospheric pressure. So there's a negative pressure which pulls the sewage and it goes into the service line. So the amount of air and the sewage which is pulled, that is controlled by the valve that is keeping the valve open. So this is how the whole process happens. So when the valve closes and when it's shut, then again the atmospheric pressure is regained. So because of this, these lines are installed in a vertical or zigzag configuration so that this vacuum which is created at the central station is maintained throughout the network. If it because of this zigzag configuration, we can maintain this vacuum throughout the network. So that is the actual reason why it is required also for this vacuum system. Right. So if you want to know more, like you can refer this document, CPHO. It's a government of India's document which is there, where they've given all details. Like for vacuum system they've given, but for other systems also, the main reasoning why the system design is like that. For instance, pressurized system, why do we design like that? All these details can be found in this document. Fine. Let's proceed further. So question 3 asks, match the following sewage collection system pattern with its characteristics. May I request Harish to take this question? Do you want to attempt this?
No, ma'am.
Okay.
Just now I joined, so I'm just trying to understand what is happening.
Okay, okay.
Yeah.
Yeah, so I think Harish and Shripad, because I don't think I've seen you for the previous classes. So basically, this is for the tutorial session. So whatever we discussed in this week, all these theory, we will try to solve certain assignment questions based on that. So these questions are mainly taken from the previous assignments. So based on this, you will be able to solve this week's assignments, and it would be easy. So since I most of the days, since like around 5 to 11 students join, so we are going following this approach that each student can take up one question and then attempt one question, and then we'll discuss more on that. So yeah, so that's how we've been going. And if you have any doubts in that also, you can ask in between. Like, let's make it more interactive. So the whole purpose. So yeah, so let's get back then. Shripad, do you want to take this question up? I mean, you can just say what you feel the answer is. It need not be right. It's absolutely fine. We're just discussing, and then we'll reason out why it's right or wrong. Okay. So Supriya, do you want to take this question up?
Yes.
Yeah.
Option A is correct.
Okay. So let's say perpendicular pattern. So you're saying it is sewers carrying stormwater are laid in such a way to seek the shortest possible path to the water course. Okay. And interceptor pattern, what is it?
E3.
Three. Sewers are
Rivers
connected.
are connected to a large size.
Okay, that carries sewage
Yes.
to a common point where it
Yes.
is disposed with. Okay, and radial pattern, you're saying it is pattern is adopted when sewage is to be disposed of on land around town, correct? And zone pattern, it is
Yeah.
suitable for sloped areas. Right. So let's go into the option. Option A is the right answer. Wait, I'll just, sorry, sorry. Just my slides just went a bit ahead. Yeah. Okay. So yeah, so option A is the right answer. So I hope this is visible. So this is what we learned in our lectures. So as Supriya was saying, yeah, so perpendicular pattern, what we do is we just take the shortest path and we move on to the nearest river body which is there. So from every point we take the shortest path. So laid in such a way that it's the shortest path possible. And this pattern is good for separate system where stormwater is disposed without any treatment. Because see, if you observe, if you need a treatment, then these are all independent perpendicular paths which are going. So if you need a treatment, then you can't have it at separate location. You'll have to take it somewhere else. So this is not suitable where you need a lot of treatment which is there, because large outlets it's difficult to set multiple STPs over there. So that's about perpendicular pattern. Then when it comes to interceptor pattern, you have something called as an interceptor, or you have sub drains which are there, which carries the water and then it pumps to the river with after treating it or without treating it, it doesn't matter. So the main idea is you have some interceptor in between which collects the water. And in radial pattern, you're giving it outside. So the option here was mainly you can give it off to the regions like surrounding towns also. Yes, because if you're radially giving it out, you won't have a water body all around, right? So if it's feasible to give it on to the surrounding city area, then radial pattern is preferred. So if you observe this side, it is going on to the irrigation fields, then other treatment fields, irrigation fields, etc. And in one side, it is going on to be disposed onto the rivers or the adjacent water body also. So that is the advantage of radial pattern. So this yeah, so in this also we need multiple STPs because it's going on to different regions. But again, you can plan where an STP is required. That is, if you're going to reuse it, then you definitely need an STP. So you can plan it accordingly. And then, if you're putting it to the water, then you may or may not have an STP. Like both practices are followed. And yeah, so this fan pattern, the question was not asked, but we have discussed this. Mainly it reduces, that is, it starts from a bigger fan and then it reduces, and finally it comes to one outlet. So that's why it's called a fan pattern. So the advantage of this is you can have a single treatment plant and everything, all the sewage lines eventually culminate at this final treatment plant. And then from there, after treating, it goes. So that is the advantage of that. So disadvantage would be that you will have to bring everything to one point, so the diameter of the sewer lines will automatically increase because of that. And zone pattern, so the option was that it can be used in sloped areas. Now why it can be used in sloped areas? It's mainly because you're zoning the region. So if you have an elevation difference, and if you have a sloped area, then this region can be considered as one zone, and for that zone you can collect it using one interceptor. So again, the interceptor is coming, but here there was only one interceptor which is collecting everything. But here we have zoned it and we have multiple interceptors for each zone. So because of that, we can segregate the region and we can have these zones. So yeah, so coming back to the question, for different slopes or different contours, we can have different zones and collect it and then supply it to the nearby body. So our pipe lift and all that pressure to be maintained, all that also becomes much more easier. Fine. So is there any doubt in this question? Shall we proceed ahead?
Yes, we can go ahead.
So next question is, which of the following statements is true concerning sewer design? So some options are given. Lateral and sub-main sewers are usually designed for average flows of the population. Sewers are designed for peak flow, and sub-main sewers are designed for average flows. Now lateral sewers are designed for average flow, and sub-sewers are designed for peak flow. Lateral and sub-main both are designed for peak flows of population. So who wants to attempt this question? Anybody? Any guesses? I think I kind of showed the answer in the when I moved across the slides. So
No, we have not seen it.
Okay, fine. Yeah. So, anybody, any guesses?
I guess
Madam, may,
yes, yes, please, you can.
Yes, Shripad.
yes, madam, main savers are designed for the average flow, and these lateral and submains are designed for this.
Okay, okay. So you're saying main, which option would that be?
Hmm,
This the second option. Is that what you're saying?
design for lateral savers are designed for the peak flow, and submains are the designed for the. No, no.
Okay.
Mains are designed for the average flow. Mains are designed for the average flow.
Yeah, so option B is what you're saying. No, mains are designed for the
Hmm.
average flow and laterals are designed for the peak flow. Right.
Yes, yes, yes.
Okay. Fine. But then if mains are designed for the average flow, like so from mains you have sub which is coming out, right? So if main is only designed for the average flow and imagine the peak time happens. So for that peak time, even if the laterals are designed for peak flow, it will not receive the like initially it has to come through the main, right? So first it'll be the main and then it'll go to the lateral or the other way. Like if uh,
No, no. Main is the last name, madam.
yeah,
Main.
main is the last.
All,
Yeah, I mean, I was talking from the treatment side. Yeah, so when
hmm.
it's coming from your residences or when you're collecting it, yeah, so it comes to the laterals first, and okay, let's go by that motion. It comes from the laterals first, and then it goes to the peak. Okay, so you're saying that if this is designed, the lateral should be designed for peak, so you can take the maximum, but main has to be designed only for average, right? But my
But the
question is,
answer is, madam. But the answer is, madam. Lateral and submain savers are usually designed for the average flow, for the population. This is the correct answer.
how do you know that is the correct answer?
No, no. Because lateral and submain savers are usually designed for the average. Lateral and submain.
Uh, okay,
That
let's
B and C. No, no. B and C is correct. Means B and C is correct.
lateral sewers are designed for peak flow and submain sewers are designed for average flow, that is B. Now C is lateral sewers are designed for average flow and submain sewers are designed for peak flow. So those both are opposite, right? So why are you saying both are right?
No, 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 madam. No. Sorry, because I am seeing the assignment and your question is different from the assignment. This is just equivalent to the assignment. Is it correct?
Okay, okay, okay. Okay, let's
That,
you're talking about this time's assignment question, is it?
this time assignment question because there is one similar question, but in that there are the two options which are correct. Okay, and in your case, in this case, now whatever the question you have shown,
Ha ha
there
ha.
the that's why I am confused. Okay.
Okay, do you remember which was the question number for that assignment?
Question number five number.
Question number 5, is it? Okay. Identify the wrong statements associated with
Right,
sewer design.
associated with the sewer design. This is just
Ah, okay. That is a multiple choice answer question. Fine. Yeah, so that question, let's leave that there. Might be. Let me not go into the answer for that one because your submission
okay.
is still due. But for this particular question, so this one it's asking which of the following is true. Okay. Like it has to be correct, not false.
Okay.
So, so finally, what are you saying? The answer is that is it okay? Let's just go by this one. Lateral. Is it peak or average? And for mains, is it peak or average? That's a question. What do you say?
Laterals are peak and main is average, madam.
Laterals are peak and main is average. Fine. So if that is happening, as we were saying, from peak, maximum is coming over here. Maximum is coming from all the peaks. But this one, mains are designed only for average. So will mains be able to accommodate all which is coming? Like, won't there be a congestion or a stagnation inside the laterals during peak
But the
hours?
pipe, but the pipe is designed as per the 1.3 times or 1.8 times. No, that is as per that formula.
Yeah, so that 1.8, yeah, that is a buffer that we're giving. That both the pipes, laterals and mains, also we take the buffer and then we design it, right? See, the whole point of laterals, if laterals are designed for peak and if it is carrying the peak, if the mains cannot accommodate the peak which is coming from all the laterals, the whole point
Yes,
of
yes.
designing that becomes redundant, right? Because then
Mhm.
might as well design this also for average, because anyway this will not be able to take. Are you with me?
Yes, yes.
Okay, so the answer to this question is that both are designed for peak flows,
Yeah. Peak
because
flows,
it
yes.
should be whatever is coming as peak, the mains and the laterals should be able to accommodate that, because otherwise, firstly, designing one for peak and one for average doesn't make sense. The other way also, if the main is for average and the peak, the laterals are for main is for peak and laterals are for average, that is also not a good design, because that much peak will never come into the mains. So that is also wrong. So ideally, both should be the same, and both we take it as peak value, so that during peak hours, this is sewer lines, right? So you don't have congestion or stagnation at any point. So we take the peak value and then design. So that is what we discussed also in our sewer design. So we have discussed this, saying that laterals and main sewers are usually designed for peak flows of the population. So that is basically the carrying capacity as per the master plan. So the design, that is what we eventually call the carrying capacity, and that is considering the peak flows of the population. Right. So anybody, any doubts in this question?
No.
Fine, let's proceed further. Okay. So design infiltration value shall be limited to a maximum of dash percentage of the design value of the sewer. So this is a very simple question directly from our lectures. So any guesses?
15%.
15.
15 or 20. I guess 15 is the first answer, second is 20.
Okay, anybody else? Any guesses? I mean, two options Supriya has guessed, so there are other two options also.
5%, I think.
5%. Wow, nice. Okay, the answer is 10%. So I think all three of you, Supriya's two guesses plus Harish's one guess. So we eliminated all the options and we got 10. So yeah, so this is, I mean, the reason is again, it's just the value which we have taken based on historic data which is there, the infiltration value. So usually design infiltration, we take a maximum of 10 percentage of the design value. But again, in the lecture, we are saying that if we have infiltration data, that is, if we have actual groundwater infiltration level based on the material, based on historic data, then we are supposed to be taking that. This is just an empirical value which we usually consider for that. Okay, so this is as per again CP HEO guidelines. It is you take a design value of 10 percentage. But yeah, so this I mean, we can just remember this, or if required, when we're actually designing, we can always go back to the standards and check. So it's not even if you're forgetting the values, it's okay. And if you're taking a higher value, also it's fine. But then you'll have to invest more. So that's one problem, right? So we're proceeding on to the next question. Which of the following does the peak factor of sewage flow depend upon? Population, population density, site topography, water supply hours. So
D. All answer is correct.
all answer, Supriya says all answer is right. Anybody else? Any difference in opinion? Okay, no difference in opinion. Yeah, all answers are right. Let's just go one by one. So population, yeah, it is important because as the you were already here, right? Okay. Yeah. So as the population increases, then more sewage will be generated. So the peak factor of flow depends. Population density also, that also matters, because the in a region, if more people are concentrated, then the sewer lines or the sewage flow which is coming from that region will also increase based on that. Site topography, we have already discussed on the zoning, how that's zoned layout is useful, because based on topography also the pipe layouts, everything has to be done. And yes, water supply hours also, because based on supply, our the use will also depend on supply. So yes, so all the options are right. It's D with all options right. Fine. Any doubts in this question? Shall we proceed further?
Yeah, please.
Yeah,
Yes, yes.
yeah. Let's proceed further. Uh, Flow rate at night is dash percentage of the average flow. Guesses?
60 to 70%.
Supriya says 60 to 70%. Harish?
40 to 50.
40 to 50%. Okay. Let's say
60 to
Shripad?
60
60
to
to
70,
70.
madam.
Okay, so this is 60 to 70%. So let's go by majority vote 60 to 70%. No, 60 to 70% is the answer. But okay, firstly, why do we take only a percentage of flow rate in the night of the average flow? Like, very simple reason. Why do we do that? Or why is this variations happening?
Because of less use.
Yeah, less use. So usually we consider that also. Like we consider slide is stuck, is it? One sec. Yeah, so we take seasonal variations and daily variations. So this is directly from the lecture. This is what we learned, and based on this, we try to reduce. That is, how much should the flow be based on different seasons, what we will be taking, and daily. So daily variation is mainly we take for during the day and during the night. So during the night, it's about 60 to 70 percentage of the average flow will only be there. Like 100 percentage of the flow will not be there. Very normal reasoning. Fine. So we are proceeding further. Which of the following method is involved in intensity, duration, frequency, curve generation? So,
Bernard equation.
so Bernard is there. Fine. Time area method, it's not there.
No.
Bernard equation.
Okay, Bernard is there. Fine. Nothing else. Nothing else, right? But we have come
Yes.
across these time area method, unit hydrograph method, rainfall runoff process simulation. What are these used for? Like these three, we have. I mean, even though we have not learned it in detail, but we have come across these terms. Am I right?
Calculation of runoff calculation.
Yeah. So runoff calculation, we have used this, and for intensity, duration, frequency, curve generation, we use the Bernard equation. So let's just not going detailed into this, but yeah, so this is what we learned for the intensity, duration, frequency relationship. So this we don't need this. So just for that explanation. And yeah, so for runoff calculation, methods of runoff calculation, we have learned this. That is, we use the rational. So time area method, unit hydrograph method, and rainfall runoff process simulation and all we use for this. Fine. So and Bernard method, that formula, we will have one problem based on that. Yeah, so we'll do that now. So, what is the rainfall intensity for a storm of 15-minute duration using the empirical formula in the absence of rainfall record? So, this empirical formula is a Bernard's formula that we're using. So, can we solve this now? What is Bernard's formula?
Oh.
It's 25.4 A by, I forgot, A by B into T.
A by T plus B.
Yes.
And what will we be getting out of this? We will be getting the intensity. Yeah, so
Yes.
intensity of rainfall. So yeah, unit is already given here. So it's millimeter per hour. That is a unit. Directly we will be getting from what is there in the option. That this is the unit. So in this, what is A and what is B and what is T?
T is the 15 minutes, A will be the 30, B 20.
Yeah, but what is it
I
basically?
guess, I hope I'm right.
No, okay, but first, without the values, what is it? What is T?
Okay.
What is A? What is B?
T is the time duration for
Okay,
rainfall,
okay,
and A and B are just taken constant for 5 to 18 minutes duration, and 5 to 20, sorry, and
huh,
20 to 100 it is taken 40 and 10 A and B values.
right,
40 and 20.
right, yeah, correct. So this is the formula that we're using, and yeah, T is the duration of storm in minutes, So that we need to take care because our option answer comes in millimeter per hour. So in case a duration was given an hour, we will need to convert it. So it is the duration of storm in minutes, and A and B are constants which depends upon the duration of the storm. So for 5 to 20 minutes, we use 30 and 10, and for 20 to 100 minutes, we use 40 and 20. So in this question, we have 15 minutes. So we will be using this 30 and 10. So let's try to solve this. So I is equal to like A divided by T plus B. And so let's substitute our into what is A? A is 30 from here. 30 divided by T, which is 15, plus B, which is 10. So can we quickly solve and come up with what is the answer for this?
.48.
Yeah, right. 30.48 millimeter per hour. So let's go back to the question. That is option A. Right. Fine. Shall we proceed further?
Yes.
Okay, great. So yeah, which of the following factors affect stormwater volume? Topography, evaporation, percolation, absorption.
All factors.
All factors affect.
No, topography.
Okay. Uh, why does topography affect? Let's reason it out. Why does topography affect?
Yeah,
There is a slope
because
that depends on slopes.
yes.
Yes, it depends on.
Slope, catchment area.
Yeah,
Slope
look.
or हाँ,
Yes, yes. Yeah,
And the other three is for losses.
three is for loss. Percolation is for
Other,
losses. Is that what you're
all
saying?
three, evaporation,
Or
percolation,
evaporation,
and
percolation, absorption, all three are basically losses. Yeah. So through this, it lose. Yeah. So this is what we learned. It's the same thing. So you take the losses as well as you take the factors affecting the catchment, and first one is for the catchment, and the other three are losses. So yeah. So that's well explained. Let's proceed further. What is partial area effect? Okay, all options are very similar but a bit like with minor variations. So, who wants to take this question up?
1 second.
Okay, Supriya, yeah, you can attempt it.
Option A is correct.
Option A is correct. Okay. Fine. Can you give the reasoning for that? Like, why do you feel option A is right? Or what is partial area effect? Can you
Uh,
explain a bit?
Actually, see, if lesser catchment area is there and rainfall is high, then
Hmm.
the volume of the collection or uh, runoff will be lesser. If the catchment area is larger and rainfall is less,
Hmm.
then water can flow, like runoff will be more. Sorry.
Runoff will be more. Then, okay. So then option A is not right, right?
Yeah, 1 second. No, option A is correct. I'm not able to give you the reasoning.
Okay.
This is somewhat similar, but I'm getting confused right now.
Yes, yes, we'll solve that confusion. Anybody else, any guesses? Do you feel anybody else? What do you think? Is it option A or B or Shripad, Harish? Oh, ML's also there. Shripad, Harish, ML, anybody? Okay, so let's see what is happening over here, and then we will try partial area effect. This is what we need to relate. So imagine we have this much of area, that this is the whole area or the overall catchment area which is there. We learned something called as time of concentration. So this is so what do we mean by time of concentration is basically the time required for water to travel from all the points, that is from so if our eventual so from even this corner, if this is our catchment that we are saying, the time required for water to travel from the most hydraulically distant location and contribute towards the catchment. That is where the point of concentration that we will be considering, the point that we are considering. So imagine I'm considering here, or the rain gauge or the runoff coefficient, which I'm taking it here. The time taken from the again hydrologically distant location, like hydrologically distant location means it involves everything. Like if it's having a high contoured, it's in a different contoured region, or a sloped region, or a different the terrain is different. So all that comes into play. It's not just the distance, but a hydrologically distant region. From there, the total time it takes to come and concentrate in this observation point, that is called the time of concentration. So this whole runoff, the maximum, the TC value that we are taking basically depends on all this. So the time of concentration, that is, this TC is the time of concentration time that we are talking about. That is what is over here. So here they're asking the amount of volume of water, basic, that is what is given over here. So the runoff coefficient into lesser catchment area into higher rainfall intensity. I'm just taking the first option, which basically means that it will have lesser time of concentration. That is, we are only considering a lesser time of concentration. Will that be greater than the runoff coefficient into the full catchment area into the lower rainfall intensity? So here we are overall talking about the volume of water that we are getting. That is what this formula is saying. That is runoff coefficient into the area into rainfall intensity, CIA. This is the formula that we have learned for surface runoff. So that is what we are calculating over here. So the question basically asks is that if I take, if my TC value or the time of concentration, that is in lesser time, if I take time of concentration to be 5 minutes, then that means probably from here that water will not reach here in 5 minutes. Maybe only this will be the circle then. Like from here, every point it can reach in 5 minutes. So probably this will be the only area that we will be considering if we are taking a lower TC value. But if you're taking a higher TC value, that is higher time of concentration, then maybe the circle is a bit bigger. That is, from far away regions also water can come and join. So based on TC value, will the surface runoff be more or less? So that is a question which is asked over here. Again, repeating, the question is, if I consider this region with high intensity of rainfall, so intensity of rainfall is given. So one is that is, I'm considering a smaller region, but the intensity is extremely high. Second one is I'm considering a larger region, but the intensity of rainfall is low. So if this is the case, so this is my second case, in which case will the overall surface runoff be higher? Or it's not that which case, is it possible that if my intensity of rainfall is high, that's the first one, but still the region of concentration is low, the overall surface runoff which I'm getting, can that be greater than the situation when the region that I'm considering is higher, but the intensity is low? That is a question. So now, does anybody want to attempt this question once more? So
lesser catchment area will give the more runoff, madam.
So you're saying this one, that is, yeah, because intensity is higher, even if the catchment area is less, because intensity is higher, it will give more.
Concentration time will be very less.
Huh. Exactly. Concentration time will be less. So you're saying it will happen. Fine. Anybody else? Any other observation you want to say? No. Okay. Yeah. So you're right. This is, and that is why we have named it as partial area effect. So it says that you don't need the whole area. That is, when the time of concentration or the concentration time is more, what happens is you're taking it from different regions, but within that time, the surface runoff that you're getting might be less. Like it need not be greater than this one. It's in all cases it need not be. There may be cases when it is greater or not, but uh, it need not be. So that is why we are calling this partial area effect. That is, we don't need the whole area to have the maximum surface runoff. So as Supriya was saying, option A is the right answer. That is when you take the runoff coefficient into the overall catchment area. So here it is a lesser catchment area that we are talking about, and higher rainfall intensity. Basically, we are talking about this lower time of concentration that can be greater than the total runoff coefficient into the full catchment area into lower rainfall intensity. So again, what is playing important? So over here is a lower rainfall intensity. Had this not been the lower rainfall, like had the intensity of rainfall been low in both the cases, then this might not hold true. So here, because in the first one, the intensity is high. When the intensity is high, it's not the area which matters, even if the area is less, because the intensity is high, the overall surface runoff can be higher. Right. Supriya, is that clear now? Hello. I'm audible, right?
Yes, you are audible.
Okay, fine. Let's proceed on to the next question. We only have a couple of questions. Yeah, so this is from the lecture that what we are discussing about partial area effect and time of concentration. So yeah, so this is the definition. Time required for water to travel from the most hydraulically distant point in the total contributing catchment to the point of concentration. So this is what I was explaining before. And yeah, so this is the relationship. This was
Ma'am,
given on option one. Yeah.
sorry. Point of concentration means the point of collecting the water.
Yeah. So basically, where we
Okay.
place our rain gauges, that is, we will
Okay.
be measuring based on that, right? So that is a
Okay.
point of concentration. Yeah,
Okay. Okay. Thank you.
fine. So let's proceed ahead. The design of pumping station depends upon space availability, distance or route of rising main alignment, estimation of design runoff at the pumping station, capacity of wet well, and additional storage capacity. So which of these? Any guesses?
Estimation of design runfall at the pumping station.
Okay, so C is there, you're saying, fine.
Uh,
You look at the option, there are multiple
Distance route
answers,
of
right?
yes. Distance route of the rising main alignment.
Okay, fine.
Space availability may not be a constraint.
Space availability may not be a constraint. Okay. If there's no space, where will you keep it? The pumping
No,
station.
yes, it is. Space availability depends on the
Generally, it is available,
design
madam.
design of the
Generally,
pumping station.
Yeah, Jem, maybe generally it is available, but in some regions, but it is an important factor. Like if it is not available, then it becomes a problem, right? Probably now it's available. Maybe years later it might not be available, right? So, and it depends on regions also. That is, there are places where due to space constraints, we might have to limit the capacity also. So we put
all the four
segregated.
factors, all the four factors are essential for the
Yeah,
design.
all the four factors are essential. Yes. Space availability is also important, and capacity of wet well. Why is capacity of what is wet well again? What is wet well?
Detention time in minutes for the peak load.
Yeah, no, wet well is not the detention time in minutes. Wet well is basically the place where you detain it. And capacity of wet well will influence the detention time. That is why capacity of well is important. That's why I put it in bracket. So, yeah, so wet well is basically before it is pumped or before it is treated, where we store it for a certain duration of time. So that capacity in the pumping station, so the capacity of wet well will also influence the pumping station, because that will depend on how much pumping is required. So, or the amount of quantity which is there. So the capacity, it depends on the detention, the capacity influences the detention time in minutes for the peak load. So that's why. Wet well is the storage unit or where we store it. And yeah, and if there's any additional storage capacity, that also influences because that much pumping is required. So the pumping station, that's also there. So yeah, so all the four options are right. Fine. Let's proceed further. Match the following stormwater drainage indices with their definition. So yeah, so who wants to attempt this question? This is again a very direct application question. Uh, Supriya, do you want to take this up?
Yes, give
Yeah.
me some time.
Sure,
I
sure.
will give you the answer.
Yeah, you can go one by one. A, which you think is right.
Drainage coverage index. It is 4, A4.
A is 4, okay.
B is
Ratio of the length of
3.
existing constructed drains to the length of total constructed drains. Correct. Yes.
B is 3.
B is 3, percentage of catchment,
C
which
is
is
2.
impervious. Yeah, permeability index, it talks about the permeability. Yeah. C is
C is 2.
natural drainage. Yeah, it is there in the answer. It's a ratio of operational natural
Yes.
drainage systems to the
Nature.
total natural drainage system. Correct. System
And
robust. Yeah.
D is 1.
Yeah, ratio of rate of incoming storm flow to the rate. Actually, D is the only one which is a bit tricky. The others, just by looking at the description itself, we'll be able to find out. But yeah, so D, the robustness index is a ratio of incoming storm flow rate to the pumping. So that comes up to option A, right? Yeah, option A, 4. Yeah, correct. So yeah, so this I have again put the answer here. Like this is what the answers are. You explained correctly. If there's no doubt, we can proceed to the next question. If any doubts? No.
No.
Yeah. So we can proceed to the next question. So, which of the following is not a component of capital cost concerning stormwater drainage projects? So, is cost of
The
civil
cost of chemicals.
cost of
Cost of
chemicals is
chemicals.
not okay. What cost is it then? Like, or chemicals are not important in stormwater drainage,
No, it doesn't come under capital cost. Capital
right?
cost will be all
It will be
design,
OPEX, right?
construction, machinery.
It will
Yeah,
be OPEX cost.
it will be operational cost, is it?
Yeah,
Operational.
okay,
Yeah,
yeah.
operational cost. Yeah, right, correct. So yeah, so all the civil machinery, drain, like whatever was infrastructure that you need initially, that comes under the capital cost, the initial investment. And chemicals are perishable materials which we need to keep, we need to keep supplying it when it's required, so they come under operational cost. Yeah. So yeah, so this is the from the lecture which was there, the capital cost, what is there, and yeah, cost of chemicals come in the operating cost or operational cost. Right. So that was again a very easy question. Let's move to the next one. So this is in fact our last question also. Water logging index is what? Ratio of encroached water bodies, area to the total area under water bodies, area inundated for 4 hours or more and having water depth more than 6 inches, ratio of total flood prone area to total area,
B,
and
madam. B, B.
percentage of catchment, which is the answer that you're saying? B.
A, B, B.
Yeah,
Area
Yeah,
area
inundated
it
for
will
inundated
4
for
hours
4 hours or more and having a water
more.
depth more than 6 inches.
6
Yeah.
inches.
Yeah, right. So it is the logging which is there. Your water is getting logged over there. Correct. So yeah, so this,
Madam, please spare some time for this IDF curve. You just explain it
yeah,
properly.
you want IDF curve to be explained. Okay. So I saw in the discussion forum, Supriya had asked a doubt. Was it not? That,
Yes, I couldn't understand
yeah,
what was that. 1 second.
yeah. So this was the slide that you had doubted,
Yes.
right? Yeah.
Intensity duration. I couldn't understand how this intensity is calculated from this table, like 116.83 with 25 mm per hour.
Got it. Got it. So that was your doubt. Harish, any specific doubt in this one? Or Shripad, you were asking, right?
Yes, sir. Related this only, madam, IDF curve.
So should I start
It's
from
very
the beginning or just
obvious.
from Supriya's how we are getting
No,
this?
beginning, madam, beginning, because that is also somewhat confusing.
Okay. So
Uh,
let's start with this slide.
All
That or
30
previous.
minutes.
This slide is fine, right? Okay, I'm starting with this slide now. So basically, this is our table or the data that we have. So here we have the duration. So this is our D. And this one, what we have, this is our intensity, that is in millimeter per hour. That is 5, 10, 15, 20. So these are the intensities which we have. And this is the frequency that we have. That is how many times this event is happening. So some of the things that we need to remember is what is a storm event. So we have, these are the terms, some terms which we're using. So storm event, basically we are talking about a rain, like you have one rain which is happening. So that is one event. So you're considering every rain or every storm to be as one event. So how many times that is repeating? That is the frequency which is given over here. So if you observe here, it is given as greater than 5, greater than 10, greater than 15. So whatever is there, we are cumulatively adding. That is when the intensity is greater than 5, uh, and the duration was about 5 minutes. It lasted for 5 minutes. Then around what 1965 times this event has happened. So this is the frequency which we have. So this is our IDF data. That is, IDF is intensity, IDF intensity, which is coming over here. D, which is our duration, and F, which is a frequency. So this is our IDF data that we have. And this usually we take from our rain gauges historical data and all that.
Madam, where is duration here? Where is duration here? Because no duration, you have given 5 minutes.
Huh.
Okay.
Huh.
5 greater than 5 is the intensity.
Yes.
Okay. So this event has happened 1965 times.
Yes.
1965 times means within which span? That is not given within 10 year, 20 year, 50
Yeah, yeah.
year.
So this one is mainly we are talking about a 29-year period. Like this is both connected actually. So the whole data that we are given is for this 29 years. So within the past 29 years, this is what has happened. And now,
Sorry, ma'am. So basically, in 29 years, the rain intensity was greater than 5
huh.
for 5 minutes, right? Am I
5 to
my
10.
under-
We can explain is that
Yeah.
5 to 10, madam? 5 to 10.
It is between, yeah, it's not exactly that 5 minutes, between 5 to 10 minutes,
Okay.
it has been this. So, in case we having like for 8 minutes, how it was, we will have to take the interpolated data from that, like in between, how much will it
Okay.
be? So that
Okay.
we will come to that. How do we do that? So this duration we have just taken it based on like certain scale. That is 5 minutes, 10 minutes. What does this happen? And so actually, if you want to see the details of that, fine, I will just stop sharing this and I will share one more, another presentation, which is the actual, where is that? One second. I'll just share the actual one, which is from Government of India. So this is from where this was taken. So there, all the detailed steps are given. So I'll just, but that is in my computer. So I'll just share that now. One second. It's chapter 3. Okay. Yeah, so one second. I'm just stopping this. Um, Stop sharing and share from this entire screen. Yeah. So my screen's visible now, right? Yeah. So if you want, you can refer this ministry's uploaded document. I'll just put this in the chat box also. So this has all the details which is there. So coming back to that, yeah. So basically there are several steps involved. So I think the confusion is because those steps are not shown. And actually because for this particular within the scope of this one, we don't need to know all that. So just because you were confused, I'm just explaining. So this is how we mainly measure. That is from the in-card, like this data we need not. So eventually we get the intensity of that. Let's start from here. So for duration, that is for 5 to 10 minutes. So then we will be measuring the rainfall intensity, like for this much duration, how much intensity. So using the knob, what you say, uh, that one we will mark how many times it is happening. So this is the initial data that we are taking. Once we take that data, then we will see for up to 5 minutes how many times it was recorded, 5 to 10 minutes how many times it was recorded. So all that we will do. Then finally we will add that up. That is, we will see add the number of storms for exceeding intensities to preceding lesser intensity storms. That is, if you observe over here, this is 5 to 10. So now we are converting this to greater than 5. So when we are converting this to greater than 5, whatever was there before also, that is for the other, and this is greater than 10. So for greater than 10, this will also get added. So like that, we add and we create one more table. So detailedly, you can go through that, how the calculation is done. So here it's explained, that is from here 5 to 10. So we add that 35, all that, and finally we get 1111. So that is what is happening over here. So we are adding all that and we are getting that value. Because see, all this we will have to add, no, when it's greater than 5. Whatever is on the right side, we will add. So for 10 to 15, whatever is on the right side, we add and we get that. So that is what is happening over here. And then the next table, when it comes, we add vertically also. So that is add the so here what is happening is, yeah. So again, so this is for or more for a period of 29 years. So we're mainly talking about 29 years, and duration in minutes we are taking. So add the number of stops for all exceeding duration preceding or lesser duration. For instance, in table, the number of stops corresponding to, so this we've already, yeah, so this is what we are adding right now, corresponding to greater than millimeter are added as 1 into 3. So this one, and that is how we get the 1965 values. Again, this you need not worry more, because we are starting from this point, because this is where our design or the IDF curve design comes. So given this data, that is if we have this data. So I took this mainly to show that this is for the 29-year period that we are having. So now based on this, again, so in this, in the question, or in our, and where is it? This one, yeah. So lecture also, we were mainly talking about a 5-year occurrence. So the data that we have is for 29 years. So now we need to, for every 5 years, what is the maximum, or what should be the threshold value that we need to take so that uh, what a storm event will happen. So that is, so we divided, that is for 30 years, we divided by 5, because 5-year occurrence is what we need. So we get 5.8. So the interpretation of that is that 5.8 times on an average, this may exceed over a period of 29. That is our rainfall might exceed the capacity of whatever we're designing for, or the storms that is there. So that is why we take this 5.8. So now what we're doing is, based on this, so 5.8 is a value that we need in order to get the actual intensity. So our overall aim is to create that intensity and duration graph. So intensity, to create that intensity duration graph, we take all the values greater than 5.8, or if 5.8 was actually there over here, we would have taken 5.8. But now whatever is greater than 5.8, we draw the bar over there. So here it's happening at 8. So which means the intensity, for an intensity of greater than 90, the duration is mostly for 5 minutes only, because greater than 8, or basically 5 to 10 minutes, it lies, because 5 and 8 is over here. So between 5 to 10 minutes it will lie. And for the next case, for the intensity greater than 75 or 75, it lies between 15 to 20. So that is the interpretation that we are getting. And here, if you observe again, 6 is over here, that is 5. So it is greater than 5.6, which 5.8, which we are considering. So yeah, so we are drawing it here. So this is the step line that we are taking. So we get the step line. So now what we need to take is the intensity. So why we are doing this approximation, so intensity, why we are doing, we are interpolating the data. Why we are doing this is mainly because it is not 5 points, we are taking 5.8, no, yeah, it is not 5.8, but it is 8. So we cannot say that it is exactly 5 minutes. It will lie somewhere between 5 minutes and 10 minutes. So that in between that value, what is that we need to find. So we can use methods like regression, like for instance, for 5 minutes, for 5, if it is 10, and for 8, the duration is 5 minutes. Basically, we take all this data, all the data that we have, and we use a regression. Like there are regression, like it's again, you're trying to fit a curve based on that, and you try to minimize the error which is happening. So based on that interpolated data, we are now saying that it is not 5 minutes, but it is about 8.5 minutes. That is because 8, yeah, it is more closer to 10 minutes, because it's lying between 5 minutes to 10 minutes, and it's more closer to 10 minutes. And how we are getting it, we need to use mathematical methods to do that. So it's so here also it's just mentioned based on interpolated data. That is how we will be getting this. So let's take another case, that is 75, intensity of 75. So here we have got intensity 75. So 8, it corresponds to 15 over here. So basically it will lie between 15 to 20 minutes, but 8 is a value which is much higher than 5.8, right? So it will again be more closer to 20 minutes. Let's see what it is. So yeah, so it is coming up to about 16.75. It is not 15 that we're taking 16.75, because the next value which was there was 2. I missed that. So the next value is 2, so which means uh, actually when you do that regression only we will get all that. So according to that regression, this is what we are getting. Let's take another example where it's very close to here. Yeah, so let's take 6. So it is very close to 5.6. In that case, so this is for 45 and you have got 75 over here. So let's see, for 45, see, it is 75.5, because it is again very close. Like you've got 6 and the value that we need is 5.8. So there's not much variation, but you're just taking 75.5. So this is what is happening over there. My
So
screen was
these
visible.
durations are, sorry to interrupt you. So these durations are calculated by regression,
Yeah,
right?
so it need not be regression alone. Any
Exact
interpolation method,
value.
yeah, any interpolation method we can use. Regression is one of the most easiest methods by which we can do that.
Okay. So calculation we are not concerned about. That's why the detailed calculation
Yeah, that
is
is where,
not.
because actually within the scope, this details we need not go into those details. That is why it is not
All right.
discussed
All
here.
right.
But if you want to
Okay.
learn, like for gate preparation and all, it might be useful. So I can share this. I will put this also in the drive where the PPTs are shared. So you can go through this chapter. So it is a verified document which is there. So if
Not
you
required now.
No, I'm saying it because it is actually very important for civil engineering point of view. It is a very important calculation also, but within the scope of
Yeah.
this what course, it's not that important. We just need to know how it's the final intensity IDF curve. How do we use the IDF curve and what it is? And in the next module, we will learn some more details on how certain calculations are done and all that. But again, whether this is coming or not, I'm not really sure. But the other methods, storm calculation methods, runoff calculation methods, those we will be learning in a bit more detail in the next one. But for this one, this module, I think this much of information is adequate enough.
Yeah, but I guess for a planner, this much information is okay because ultimately the drainage engineer do the design calculation
Yeah,
and all.
that's also there, but it's always good to know more also, that there's no harm in that. So yeah,
Yeah, that's right.
did I answer? Or Shripad, was that clear to you? Or is there any more doubt?
That is clear, madam.
Hmm.
Okay. But once again, that uppermost curve, na, idea
Huh.
of curve, this you have explained.
Huh.
But the first, you just go for a second in the first one.
Okay, one
There are
second.
two.
Yeah, so this is, yeah, so
That
this
is
is,
rainfall
huh.
intensity duration frequency relationship.
Is my screen not visible?
No, that is visible.
Huh.
I open another screen here. Okay.
Shripad, hello?
Yes, now it is
Yeah.
visible.
Yeah, so you were saying
One screen above this one. There are two screens, na,
this one,
above this one. Above this one.
the rainfall intensity duration frequency relationship, that slide?
Relationship. Yes, yes.
Okay. Yeah, so what is your doubt here?
No, you just explain it, madam, because right now, uh, last week I have seen. Now you have explained, na.
Ah,
That is that is true now. What you have explained, that is okay. Okay,
okay.
but these first two slides,
Huh.
that I am not getting.
one more curve is there before this slide. If
Before
you
this, right? One
This
more curve
one,
is
okay.
this
where,
one.
yeah, where 30 years, 20 years. Yes, correct. Right.
Yeah, okay. This is okay. This is basically again based on the data that we are collecting. This is just the intensity or the duration and the intensity curve. So this is here we have the intensity and here we have the duration. So it's basically an ID curve, and our frequency is again coming over here, 40 year, 30 years, 20 year. So what you mean by this the 5 year, all that is basically the return period. We were talking about return period, right? So it is the time when that storm would repeat, or we can expect the same behavior to happen. For instance, if you're taking a 5 year period, that means you're doing all the calculations considering a 5 year period, then we need to follow this particular curve. If you're following a 10 year period, then you follow a different curve. Now, why this is happening? Again, it links back to the previous one. I'm just going back to this slide. So here we have taken it for a 5 year period. So as I said, we took the number of years which was there, 29 divided by 5 we took. If you want a 10 year period, then we will take 29 divided by 10, because within that 10 years, how much it's happening. Uh, Mainly what is the return period and all that is doing is so that we are designing or we are calculating the pipes, all those design requirements. So for that, we will be using this. So if it is a 10 year period that we are calculating, then again, all this value will change. So if you take 10, then it'll be 2.9, which means anything greater than 3 will be taking. So which means, sorry, anything greater than 2.9. So which means this curve will again change. It will, it'll be something like this. So the value that we are getting here, or the step that we are drawing, that will also change probably. Yeah, it'll be something like this. So based on this, all this interpolated data will also change. And this interpolated data, if I again plot as in, so this is again, this is the curve which we got from that. That is, you have the
But what is
duration
the,
over here and the intensity over here.
madam, what is the standard procedure of the occurrence? That is 5 year or 25 year? Generally, it is taking 25 years, na? Recurrence period.
No, that depends upon, yeah. So we have learned that design period usually we can take for like 30 years, 25 years, all that. So that recurrent, you can take multiple years. That is the reason why you have all this multiple data which is given, right? So it depends on the use that you're putting into. So certain regions where there is heavy, high intensity, then you might go for a lesser or higher duration based on intensity. So that is very subjective. You cannot generally say that I will take for this many years only, because you're considering stormwater. So regions where rainfall intensity is higher, you might have to take the frequency period based on that. Sorry, the return period based on that also, right?
And what is the representation of area? Area representation. This is a where the gauges are,
Area
where the rainfall.
representation, yeah. So we learned the Thessian method of calculating what is the area, right? That is, you make Thessian polygons or Voronoi polygons, and based on that, you calculate how much of area comes under that rain gauge. Remember that in one of the initial lectures we had? So imagine you have that area and you have certain rain gauges, then we draw perpendiculars between them, and then we try to cut them, and then we say that, okay, so this much area will come into this rain gauge, this much area will come into this rain gauge.
Okay.
You might want to revisit the initial lectures. There, detailed explanation is given, or you can just look into this Thessian method of division, or it's also called the Voronoi method. You basically draw these Voronoi diagrams or Thessian polygons, and you demarcate the area which each rain god serves. So I hope this curve, whatever you asked, is clear. Like why we are getting different curves for different years, because it's based on that intensity graph that we are drawing. Is that
Okay.
clear now?
But generally it is calculated for the cities. So that's why there may be some limited rain gauges depending on the population.
Yes, yes. So okay, if you want me to explain that, it's basically that you have a city area, and if you have only one rain gauge over here, and you don't have anything, then the entire area is for that. Now, if you have multiple rain gauges, and this need not be, as you said, it need not be equally paced. It can be in different regions. So I've got 1, 2, 3, 4, 5 rain gauges. Imagine this is the case. Now the amount or the catchment area for each rain gauge is calculated by we draw perpendiculars. That is from this rain, the nearest rain gauge, we draw perpendiculars and we bisect them. So this is the bisector for this. This is the bisector for this. So which means area region 1 will be served, like rain gauge 1 will cater
Okay.
to all of this. And for 2 also, so between 2 and 3 I'm drawing a bisector. So 2 will cater to something like this. And 3 and 4 I'm drawing a bisector. So this will cater to some region like this. And 4 and 5 I'm drawing, so this will. So it need not be what do you say, an equal area which is being served. It can be like, for instance, 5 is serving a larger area, whereas 3 is now serving a very small area, because there is another something, it'll be something like this.
Okay,
Yeah,
got
so
it,
the,
madam.
got it, right? Fine. So any other doubts?
Madam, only one thing is that whatever the meeting is scheduled, that should be put on the that is in the Google Meet, so that we will be noticed as a meeting, because
Yeah,
generally
but
whatever, because all these live classes I have missed only because of that.
you were
We are
getting
not
email
getting
notification, right?
no email notification we are getting, madam, but most of the time we miss the checking email also.
No,
Acha.
we
Put
get
in the
what
calendar. If you put in the
notification
calendar,
also.
that is the best practice, because always we
Yeah,
get
that's
reported.
right. But we get the WhatsApp notification also.
The WhatsApp I am not receiving. That's
Okay,
why I miss
okay.
all the.
Do you have like how do you get a WhatsApp notification, Supriya? Even I'm not familiar with this. Is it a personal, or are you part of
I
some
don't
group?
know. It's on NPTEL. The
No, no,
first two
personal,
lectures,
no?
yeah, first two lecture I went.
Personal
No, it's
notification.
NPTEL.
No, I'm asking,
Sorry.
NPTEL sends you personally, or are you part of some group like NPTEL,
Uh,
this group?
no, yes, it's personal. The first notification I got on 15 August. Before
Okay.
that, I also missed the first and second, and due to this WhatsApp group only, I am able to attend it, because I know. Otherwise, now I am knowing the timing and the days people
Acha.
are taking the live.
Okay,
But
okay.
the first session,
Because
second
yesterday
session, I
also
missed it
I
because
miss this live session.
Yeah, so actually, in a week, you can attend any one live session. Yeah, you need not attend Mondays and Tuesdays. Both are not required, because more or less it's
Okay.
repetition only. For every
Sure.
course, we have one live session. That is the actual schedule. But since for this particular course, multiple people had registered, like the registration was very high, like around 900 students have registered, 800 something, 800 to 900. So that is why we're keeping two live sessions, because we expected a lot of crowd. So it's a repetition actually. So you can attend any one, that is enough. So I'm telling you, it's every Monday 7 to 8 and every Tuesday 7 to 8. Any one you can choose. And it will continue till 19th August. I think 29th August or something is your exam. So 19th August will be our last week's, like week 12's discussion. And
29 September. 29 September.
sorry, September. Yeah. So not September, October. 29th
October.
October is your, my bad. Yeah, 29th October is your exam. And by 19th, I think all the modules will be over. 19th October. So yeah, so you can keep this in mind. And yeah, so this I'll bring to the notice of NPTEL also, that yeah, if you can get a Google can remind you like calendar notification, yeah, that would be good.
Yes, calendar notification is required.
Hmm.
Okay.
excuse me, have you done the register exam?
Yes.
I think after I registered for exam, I'm getting the notification for these live classes.
No, we have registered for the exam. Exam we have registered. Offline exam.
Yeah, no. Okay. Then also you're not getting. I don't know why they can only answer.
And one thing
Yeah.
is, madam, for the civil engineers, because I have passed the civil engineering in 1993. What we
Okay.
studied at that time and this course is different, because right now we are not familiar. Just I am from the road and infrastructure division. That's
Okay.
why I am more interested in this field.
Okay.
But it is somewhat different now from the civil
Yeah, so this
engineering,
is actually a
environmental.
mix. So yeah, for instance, this IDF calculation and all, I think it is current
It was
civil
there.
engineering syllabus has
Yes.
these. It is very important subject also. I think there's one dedicated subject also as rainfall calculation and all that.
Yes.
Yes. So
But almost almost all these 12 weeks are covered in civil engineering already in the existing syllabus? Because right now I am not familiar with the existing civil engineering syllabus.
Yes, yes, yes. So yeah, so I think a lot of topics like that
But
are
this course
mixed
is
in.
planning.
Yeah, no, but civil engineers can, it is meant for, it is a planning course at a master's level planning course actually, but then our targeted audience is both civil engineers, architects, practicing planners, uh, and
Yeah,
yeah,
right,
so that's
right.
there.
Uh, but it is not more into the engineering and calculation part that I am telling.
Yeah, yeah, it is,
That this course is more about the planning part and less about the civil engineering,
okay.
because the calculation and all is very less. I can see here. I'm a planner, but I have more than 5 years of experience working in infrastructure, thing utilities, and line infrastructure. So that's why I can relate it.
Okay, okay, okay. Yeah, that is true. Next week we'll have some
But
more
that can
numericals and
help
all.
the civil engineers more.
Yeah, yeah,
Okay, thank you very much.
yeah. Okay. Yeah. Thank you. See you all next week, then next Tuesday. Bye.
Bye,
Thank
good
you.
night.
Thank you. Bye.
Bye.